Willkommen. Bienvenue. Welcome. Hodor. My name is Stuart Marks. Thanks for coming. I work in the Oracle JDK Core Libraries group, and this is a talk about the new collections APIs in Java 9. I am going to be talking about future development in Java 9, and so everything I say in this talk is subject to change. So this is a companion talk to a talk I gave a couple weeks ago at Java 1. That talk was entitled New Tricks for Old Dogs. It's a joint talk I gave with Mike Dwigo. That was a talk about a set of enhancements we made to collections for Java 8. And so that was intended to be paired with this talk, which is about enhancements for Java 9. And so Mike is a dog lover, and so he entitled that talk New Tricks for Old Dogs. And this one is about young pups, which is new little collections that are being developed for Java 9. Now, if you look at what's going on in these releases, Java 9, Lambda and streams, heard a lot about that, and you're continuing to hear a lot about that. Now in Java 9, there's modules, but there's still the collections framework, which is a pretty old framework, and it's still very, very much in use. And so we're still working on that. We're making enhancements, improvements, and maintenance on it. So that's what the theme of this is. It's still very important to work on, and we're continuing to enhance it. I've created a hashtag for this talk. It is Java Young Pups. I'm not going to be monitoring Twitter myself during the talk, but if you have comments, questions, or feedback, I'd appreciate your tweets on it, and if possible, I'll get you replies and information after the talk. All right, so let's start off with the proposal itself, but actually before the proposal, some history that's leading up to where the proposal ended up. So the topic is collection literals. And so if you look at other programming languages, they have a concept of collection literals. So for instance, in Python, it's very easy to create lists, sets, and dict objects, which are Python's equivalent of maps. And so a string list, use the bracket notation to create a list of strings. A string set, you can use curly braces, and a string dict has curly braces, but it has a colon separating the key value pairs. And that's really nice, and Python's a nice programming language, and that's a nice feature of it. But in Java, we have to suffer through this really verbose way of creating collections. So if we want to create a list of strings, probably the most convenient way to do that is using arrays.asList. And so that takes an array or var args of string values, and that's not too bad, but it's not too good either, quite frankly. If you want to create a set of strings, well, actually, the best way to do that is to first create a list and then pass that to the copy constructor of something like a hash set. So that's kind of roundabout. But the real pain comes with maps, because you have to create a map instance and then add things to it. And so that makes your code really verbose. So why should Java have to suffer through this verbose syntax for doing something that in other languages is very convenient? So we have tried to solve this problem in the past. And so if you remember, Project Coin was something that went on a number of years ago during the development of Java 7. So the idea of Project Coin was that it was a set of proposals for small change to the Java programming language. And so one of the proposals that was floated at the time, back in early 2009, was on collection literals, and that was proposed by Josh Block. He's the author of Effective Java, and he's also the author of the collections framework, which was introduced back in 1.2. So Josh seems like kind of the guy to introduce collection literals into the language. And so that proposal was floated again in 2009 during Project Coin. So the proposal was actually remarkably similar to Python's. At least in syntax. Now what it actually did, of course, there was a whole bunch of things that were necessary to deal with how that syntax dealt with Java collections, but I'm not going to go into the details of that. There was much interest in this. This is a great feature. Everybody has wanted it for a long time. There was lots of discussion on the mailing list, mostly about syntax, as it turns out, of course. And also, at the time, if you go read through the articles, which I did recently, is that an alternative to proposing a language syntax was a library-only API for creating collections. And so this was discussed all the way back then. And the question there was, do we need a special syntax changing the programming language, and is it worth the cost of changing the programming language, or should we just go with a library-based proposal? So that was discussed, but that never went anywhere. And in fact, the whole collections literals proposals never actually went anywhere in Project Coin. There was a lot of interest and discussion in it, but I think basically what happened was that they ran out of time. Josh himself spent a lot of time working on Try with Resources, which did get into Project Coin and thereby Java 7, but there just was not enough time left and not enough expertise and personnel to implement collection literals in Java 7. So that got dropped. And so most importantly, nothing happened. The collection literal syntax was not introduced, neither was any kind of library-based API for it. There was another attempt at this more recently in early 2014. So that was, I guess, about a year and a half ago at this point. This was at the tail end of Java 8 development, and the team started looking at new features to introduce in future JDK releases. And so collection literals was one of the things that was left over from Project Coin. So it became natural to say, okay, let's revisit this and take a look at this again. Now, there were okay, so actually a little bit of background here. So this is JEP 186. JEP is a JDK enhancement proposal. So this is the framework and process that we're using now for working on enhancements to OpenJDK. And so JEP 186 was what we called a research JEP. And so it was not actually a JEP to develop the feature, it was a JEP to investigate whether it was reasonable to develop the feature. So it's a bit of it's a bit of meta project there. But given that language changes and stuff generate lots of discussions and they tend to go around in circles a lot, I think it made a lot of sense to do a research JEP to explore the space, to determine whether it was feasible, and then if it was determined to be feasible, then go off in a particular direction. So there were actually two, I guess I would divide this down into two major approaches for how to proceed with collection literals. One was actually very similar to Josh Bloch's earlier Project Coin proposal, which was to develop a syntax and have that syntax be bound directly to particular concrete classes in the library. Now, those classes might be public or private, that's kind of a detail, but the point is you have a language feature that is bound directly to concrete classes in the library. On the other hand, the alternative was a more general extensible approach, which was to say a collection literal is actually some kind of abstract way of specifying an aggregation, and then what happens is at runtime somehow this abstraction of an aggregation is handed to a builder for some arbitrary collection, which might be a list or set of map or something else, possibly even an collections interface that hasn't been implemented yet or hasn't been defined yet. And possibly not even part of the JDK. So this is kind of the fully general extensible approach to collection literals. So after not that much discussion and investigation of this first simpler approach, this was rejected because the way Brian Getz put it in a mail on one of the OpenJDK mailing lists was something that was bound to built-in types in the JDK would be disappointing. And so there's a group of people who wanted something like collection literals to apply to new collection libraries that they were developing, separate from the JDK. So, gee, it makes a lot of sense that they would be disappointed. You can't use this great new syntax if they're bound directly to concrete implementations that are JDK specific. But what that brought to the surface was this idea that the architecture of Java is to have the programming language and the class library kind of be at arm's length. So this is an example of the loose coupling principle. In general, Java, the programming language, tries very hard not to have too many interdependencies with the class library. And so there definitely are some, and they primarily, but not exclusively, they primarily reside in the java.lang package. That's the significance of that package, which is it's part of the class library, but it is intimately bound with the language. But most of the rest of the class library is separately defined, and in principle you can replace the class library with something else and it would not affect the Java programming language. So adding something to the programming language that says, oh, okay, these collection classes over here, these specific concrete collection classes are now baked directly into the programming language, that would make the language much more tightly coupled with the library, and that caused people great discomfort. So there was resistance to doing that, and so that's why this simpler approach, even though it has many attractions to it, that's why this simpler approach was not pursued. Now there's this more general approach, which is to make it flexible and extensible, and you can not only create a list setter map, but any collection interface or something that hasn't been invented yet, or some third-party library. Well, when you try to do that, it makes things really complicated, because people think of collection libraries that haven't been invented yet, and they say, we want the builder that to be able to consume things in a particular way. And so the language has to accommodate things, it has to accommodate libraries that haven't been invented yet. And so that's very, very difficult, and it's very complicated. And what happened was, there are ways to do it. There's certainly ways to do it. It's not that it's an impossible task. What happened was, things got very complicated, but then we left behind this nice, clean, simple syntax of saying, oh, I want a list, bracket A, comma, B, comma, C. So that went by the wayside because you needed to specify, okay, is this a linear list or is it a set of pairs or something like that? And then you needed to specify how that was going to be passed to a builder of the programmer's choice and so forth. So it became very messy, as Brian Getz said. It became so messy that it was going to overrun its design budget. So it's not that it's impossible to do, it's just that it's a cost-benefit trade-off. So yeah, we could go off and design this very complicated, very general, very flexible mechanism for collection literals, but it would be at great cost. And you know, as painful as it is, maybe it's not giving us what the benefits that we want. In particular, it would have taken a lot of time away from value types, which you may have heard Brian Getz talk at other conferences. It's a very important feature that's required a lot of attention. And so, in fact, doing something like this would have been a distraction from that, and that was not an approach that they wanted to pursue. So based on this, instead of designing an extension to the programming language, they said, okay, let's revisit this idea of a library-based solution. And what Brian said at the time was, it gives us X% of the benefit for 1% of the cost, where X is much larger than 1. And so I think that's true. And so what I did was, maybe the third time is the charm now, so I've filed JEP 269, which is a library-based API to replace collection literals. So I think that's true. I think we can get about 80% of the benefits of a language-based syntax for collection literals by pursuing pure library APIs with no language changes. Now, maybe in the future, with value types coming along, we might have some different syntaxes proposed for value types, but not at this time. So for what we're targeting for JDK 9, or at least I hope to target, is that we get a set of library APIs that functionally replace collection literals with no language changes whatsoever. And in fact, so that's true. We get most of the benefit at a tiny fraction of the cost. Basically, I'm the only guy working on it, and I think I can make pretty good progress and probably get something into JDK 9. Whereas if you have a language change, it requires the compiler people, the spec people, a bunch of architecture, and a whole bunch of discussion and stuff, and it might not converge. And in fact, we've had 2 instances in the past where it really did not converge. So I think we have a good chance of making a lot of headway. The current status is that JEP 269 is proposed to target, so I think that means it's likely to get into JDK 9, but of course, you know, I can't make predictions about the future. I have a draft API out for review, actually 2 drafts, and then there's a proposed, there's a sample implementation in the sandbox for JDK9. So it's not committed yet, but there is code there, and basically, the fact is it's not that complicated. Basically, I have something that works pretty well. All right, so let me go over the API that we're proposing to add. So the goal is, it's an API, but the goal is to be very similar to what the goal of collection literals was. So we want things to be simple and concise and brief and convenient, but we are not trying to be very general. So in particular, we can produce instances of list, set, and map. And so we're not going to try to tackle, create a list of, or create a collection of some arbitrary type. The API is pretty simple. I'll show some examples on the next page, but the main thing we do is we're using a new Java 8 feature, which is the ability to add static methods to interfaces. So we use that all over the place. Now, I think one of the things that I found surprising actually was this is a real simple API, and the number of issues that actually arise when you try to look at it and define it is surprisingly high. In fact, the bulk of this talk is not about the APIs themselves, but the design decisions that went on behind it. And then there are also a large number of implementation issues. It's very simple to come up with an implementation, but do you want the best implementation, or do you want a better one than the simplest one might be? And so there are lots of interesting issues there. So I'll cover some of those in the talk as well. All right, so here's the API, mostly on one slide. So it's a set of static methods being added to the list, set, and map interfaces. We are adding a set of static factory methods, list.of, containing a bunch of fixed argument overloads, so 0 through 10 arguments. So there's actually, if you look at the proposed Java doc, it's basically list.of e, comma, e, comma, e. So it's a little bit verbose there, but the fact is, what it allows you to do is write out a fixed set of arguments and pass it to list.of, and it creates a list with exactly that number of elements. In addition, if you want to create a list with more than 10 elements, there is a varargs overload, so you can pass an arbitrary number of elements to list.of. All right? So the same thing with set.of, 0 through 10 fixed arguments plus a varargs overload of set.of. Map is a little bit different. So maps, instead of being what we say is a linear collection of elements of a single type, it contains key value pairs that are of a different type. And so in order to make things convenient, we're providing a fixed arg set of overloads for map up to 10 key value pairs. Now, if you want more than 10 pairs, we have a problem. And so what we settled on was map.ofEntries with a varargs parameter of map.entries. And so we created a convenient way to create map.entry objects. I'll talk a little bit more about that later. All right, so let's revisit our examples. So in the original, in classic Java code, if you wanted to create a list, a set, and a map, the code at the top of the slide shows you how to do that. Now, under the doing more or less the equivalent thing, although there are some differences I'll get into later, but the creating list, set, and map that have the same contents as those shown above is much simpler. So we have list.of a, comma, b, comma, c, same with set, and then with a map we have alternating key and value pairs, alternating keys and values, which are of different types. Now, if you want more than 10 key value pairs in a map, then what you can do is specify a set of map entries, and we've created a static factory method entry that can create a map entry for you. And so that takes 2 parameters, a key and a value, and then you can provide a list of an arbitrary number of those and pass that to map.ofEntries. All right, so basically that's the API. So we're done, right? Okay, hey, 40 minutes left. Okay, now, no, the rest of the talk is about the design and implementation issues. So there's a lot of stuff going on under the covers. So I think the first thing is, how do you deal with maps? And coming up with the map.ofEntries API actually involved a lot of thinking and discussion. So if you look at list and set, they're real simple because you can have a certain number of fixed arguments and then say varargs. And varargs works pretty well for those. But for map, the problem is the keys and values are potentially of different types. And so you can't have a method with two varargs parameters. And you don't want to have a varargs parameter that is common to the type of the key and value pairs. You might as well, basically that would end up being a varargs of object, and it wouldn't be type safe anymore. So there's a big wrestling match we had with the language here in order to figure out how to pass an arbitrary number of keys and values to the map factory. But I came up with a set of criteria for what we wanted to look for in an API. So the first is that it had to be as simple as possible because, again, we're modeling collection literals except in a library API. I think the very important thing that's very easy to overlook is that it needs to be compile time type safe. Java is a statically typed language, and coming up with an API that was not statically type safe, like a varargs array of objects, that would be a pretty lousy API, and that would stick out very poorly from the rest of the APIs in the library. So having it be type safe is very important. So here's a subtle one, which is we wanted the number of key value pairs to be known at compile time. And so varargs has that property. When you call a varargs method, what happens is the callee gets an array, and the array is of the exact right length, which matches the number of arguments. So there are a variety of patterns, like builder patterns, where you repeatedly call add or something like that, that we considered. But the problem is there that it would require some kind of extensible or growable data structure. And certainly possible to do that, but that's a disadvantage because it would require extra copying at creation time. So a subtle point about the API is that we wanted the key and the value to be adjacent in the source code. So one of the alternatives was have an array of keys and an array of values. But if you have a bunch of those and they stop fitting on a line, then it becomes really hard to match up keys and values. So we wanted those adjacent. And then finally, we wanted to avoid boxing if at all possible. Okay, so as I said, our solution, at least to most of the problems, was to come up with a static factory method map.ofEntries, which takes a vararg parameter of map.entry objects. Now, creating a map.entry object is actually kind of cumbersome. So if you've done this before, there's actually an implementation in the JDK already. It's called abstract map.simple immutable entry. And so that's a real mouthful. So what we did is we created a new static factory simply called entry. It's on the map interface, and it takes a key and a value. And so basically call that to create a map entry, and then call that successively and pass those values to map.ofEntries. Now, it works pretty well, as you saw in the example on an earlier slide, but it does unfortunately have the characteristic that it boxes the key and the value into a new object, which is immediately unboxed by the factory method and thrown away. So that creates more garbage than we would like at creation time. But maybe, just maybe, when value types come along, it might be possible to make the return value of the entry method be a value type. And so if you look at what's going on in future Java development, is to come up with a new kind of thing in Java called a value type that does not involve allocation on the heap. So we might be able to do that, and so we're kind of carefully tuning this to make sure that we don't make it impossible to change this into a value type in the future. Overall, I think we've met most of the criteria. Did Did I? Oh, I missed my tagline on the previous slide. So when we looked at all the different alternatives, basically our conclusion was they all suck. So what we ended up with was, I think this is a compromise that sucks the least. So I think it works. It works okay. It's not the best thing that's possible. This is the area where if we had some special support from the language to have some kind of syntax for specifying a pair, that's where this would have come in really handy. But since we didn't want to change the programming language of the syntax, okay, well, so this is what we'll come up with, and this is what we'll live with. All right, so moving on. So I mentioned that the API has a set of overloads, and one of the problems with overloads is that, especially if you have overloads with the same number of arguments, if you pass a null, that is ambiguous. And so if you say, what happens if you say list.of null? So the compiler will look through the API and say, there are two matches. There's one which takes a single argument, list of E. And then it also matches list.of varargs of E. And so in fact, when the compiler encounters an ambiguity like this, it's a compile time error. It's not a warning, it's actually an error. So if you say list.of null, your program will not compile. Okay, that seems like a big problem. Well, actually, we've basically finessed it. We're not allowing nulls in these collections, so you're never going to want to say list.of null anyway. So yeah, this is ambiguous, but sorry, we don't care. So I'll have more to say about nulls later. So actually, the thing about API design and the programming language is that overload resolution is probably the most complicated area that library designers have to deal with. This is a real pain. And so there's a lot of discussion about dealing with overload resolution with lambdas. This isn't quite as bad, but there are a number of subtle issues that arise. So here's another one, which is, what happens if you pass an array to list.of and pass it a single argument? Well, that's sort of similar, because that could, well, I'll just go by the example here. Suppose you create an array of strings, and then you pass that to list.of. So it's kind of similar to list.null, but if you pass an array, then it still matches two things. So that could mean, if you pass an array of 3 strings to list.of, what could that mean? It could mean 2 things. It could mean create a list that contains 3 strings, or it could mean create a list containing 1 element, which is the string array itself. And so which is it? So it turns out that because of the overload resolution rules, the varargs overload is preferred because it's more specific, et cetera. I don't know all the. I've tried to read the section of the language specification that covers this, and frankly, I don't understand it fully. So, but in any case, what happens is that it ends up calling the varargs method, and I think you actually get the right result. If you pass an array of 3 strings to list.of, that's like passing 3 strings directly in the argument list, and you get a list of 3 strings. Okay, that's great. In fact, you don't even get any warnings there when you do that. The overload resolution unambiguously selects that particular overload, and that's what you get. Now, sometimes you might say, okay, well, gee, I want to create a list that actually contains an array. How do you do that? Well, first, I have to say that really seems like an edge case, because mixing lists and arrays is kind of a funny thing to do. So if you really want to do that, maybe you should consider creating a list of lists instead of a list of arrays. But sometimes there's a need to create a list of arrays, and you can do that. What you have to do is you have to specify the actual type of the list you want in a type witness. So there's this funny syntax here, list.of open bracket string array close bracket, and that will select the other overload, so you can actually create a list of arrays if you wanted to do that. Now this only happens if you have 1 element. If you actually have multiple arrays, it actually works just fine. So this is real special case. So this is kind of an ugly workaround, but I think it's a rare enough case that it's like, hey, you're doing something kind of weird, let's just document that this is the way to do it and move on. All right, so there's another design question, which is, how many fixed arg overloads should there be? And so it's really hard to come up with a good answer. And in fact, I've changed the proposal a couple times, and I get criticism no matter what. So I think we just have to decide. But I think one thing that's useful is that the guys at Google who developed the Guava library have something similar. They have static factory methods that have fixed arg overloads. And what's interesting is they've for their list factory, they have 11 fixed arguments and 5 for set and 5 key value pairs for map. And so I asked them about that, and there was a bunch of back and forth, and it was sort of, it's basically arbitrary. And at one point, the answer was, this one goes to 11. So that's how they ended up with 11. So one thing they did, though, is they did an analysis of the number of uses of collection sizes in their code base and found that there's a fairly steep drop-off in terms of the number of arguments. That is, if you add more arguments, the frequency of usage drops off. Initially, it looks like it's exponential, but I'm not sure I believe that. But it does drop off fairly steeply. And so, somewhat arbitrarily, I just said, okay, let's just use 10, because I think an early proposal had 5, and there were enough cases where we wanted to, there were enough cases that seemed to occur that exceeded that limit, so somewhat arbitrarily I chose 10, and so that's the way the proposal stands now. Now I'm saying, now I'm hearing feedback like, oh, that's too many, or actually you don't need those at all, but you know how that goes. So anyway, but my intent in choosing a rather high number is that most of the cases, and I'm not sure how most is, but I think it's upwards of 95%, should be caught by using the fixed arg overloads. And then there's always the failover to the var args methods if you have more than that number. But I think we want to capture most of the use cases using fixed arguments. All right, earlier I promised to talk about nulls. And so the new collections implementations will disallow nulls entirely. So if you try to pass a null as a member of a list or set, or as a key or value of a map, you'll get null pointer exception. And so I think in retrospect, I think it's somewhat controversial because people actually use nulls this way, but in retrospect, at least from the API design standpoint, allowing nulls as members of collections in the original collections framework was generally regarded as a mistake. And you can see that because the early collections, like ArrayList and so forth, allowed them as nulls, and so new collections were added in 1.3 and 1.4, and those all allowed nulls. But something happened in Java 5. And in fact, I think it was driven by the concurrency stuff. Basically, the concurrency utilities disallowed nulls in all the concurrent collections. And in fact, even in new collections that were not part of the concurrency package in Java 5, disallowed nulls. And so that set a precedent, which I think we're going to stick to here, which is every collection added in Java 5 and beyond has prohibited nulls. So I'm not going to be the one to turn that around. So why are we doing this? Well, nulls are bad. How much more can you say about it? But there are actually some practical issues with it as well, because nulls really, allowing nulls as members of collections really complicates your API. So for instance, the issue that I think most people are familiar with is map.get. And so map.get can return null. Well, that can actually mean two things. If the map allows nulls as members, it might mean there's a key there whose value is null that's present in the map. Or it might mean there's nothing present in, that key is not present in the map at all. And that's kind of a problem. You have to make another API call to disambiguate that. Now, if you have a map that doesn't allow null values, then it's unambiguous. Map.get returning null means, hey, there's no key in there. Now, it gets worse with things like map.compute, which is a new Java 8 API that takes a lambda that computes a new value for a map. And that actually uses null as a special case to mean that an entry is not present, or that if the return value of the lambda function you pass in, if that returns null, it means the entry should be deleted. So if you allow nulls as map values, then if you want to delete something, instead of making the value be null, you have to really complicate your API to accommodate that. And so So that's from the API standpoint, where using null as a special case is very useful, and allowing null as an actual collection element is a real problem. Now, it's also useful in internal implementations, and so it's used all over the place in collections implementations to mean the absence of a value. So if you have like for instance, if you have like an array which is a table used for hashing, if there's null there, that means, gee, there's nothing there, and so you can immediately terminate your search. But if null is a valid member, then you have to do a bunch of special casing in the implementation, and that, well, one, that's error prone and it's a maintenance issue, but it actually also slows everything down. And so anyway, for those reasons, we're not allowing nulls. All right, and so this is sort of like burying the lead here, because one of the things that's a prominent issue with the new collections, which I haven't mentioned until now, halfway through the talk, is that the returned collections will all be immutable. And so this is kind of interesting, because people who've been working in collections have been wanting this for a very long time. But it actually also comes as a surprise to many people. So I should clarify at this point that I'm talking about what I'll call conventional immutability. So what that means is if you say list.of something, then the list.add, remove, and set methods will throw unsupported operation exception. So we're not going to do something like an immutable persistent collection, where if you so-called modify it, you get back a new list that shares structure or anything like that. So we're not doing anything. These are conventional immutable collections that reject requests to change them. So why are we doing this? Well, immutability is good. Turns out that there's a very common case of if you're working, if you have some program, it's a very common case to create and initialize a collection with a known fixed set of values and then never touch it thereafter. And so it would be nice if to say, okay, well, if you know you're never going to touch it thereafter, then you can make that collection actually be immutable instead of just sort of not modified by convention. And so that's particularly useful as initializers in static final fields. Another thing about immutable structures is that they're automatically thread safe. So once you've created one of these immutable collections, then you can hand it off to threads safely, and all of them will see consistent views of that collection. You don't have to do anything special to do that. Now, I'll talk more about this later, but if you make a data structure immutable, then you don't have to have the support in the data structure itself to accommodate future mutability. So it's one thing to say, gee, I'm going to create a hash set and never modify it. But if you know you're never going to modify it, if you issue a different library call, then the library can do something much, much, much more efficient. And so I'll have some more slides on that later. And then finally, there's been this dull roar over a while, which is the demand for immutable collections in the JDK. And so various third-party libraries have provided immutable collections, but the JDK has, up till now, not had any immutable collection implementations. So here they are. The JDK does have what are known as the unmodifiable wrappers. So if you wanted an unmodifiable list, you could say collections.unmodifiable list and pass a list to it. But that only provides an unmodifiable view. The underlying list is still modifiable, and modifications to it are visible through the thing returned from unmodifiable list. So it's not actually immutable at all. You can sort of get immutability by creating a list, wrapping it, and then throwing away the original one, but you have to make sure to throw it away, because if you accidentally leak that reference, then that actually can become a security hole, because it's not actually immutable. Okay, so here's another design decision that I thought would generate a lot of controversy, but it was a surprisingly quick agreement on this. What happens if you are constructing a set or a map and you have duplicate elements for the set or duplicate keys for the map? And so I did a survey of a bunch of different programming languages, and it turns out that most of them will have some policy like last one wins. And I found this kind of surprising, because I think if you're writing out elements in a literal and they're duplicates, that's probably a programming error. And so ideally, if we had a situation where we had a collection literal and all of the elements were compile time constants, the compiler would say, oh, okay, I've detected a duplicate, and make that be a compile time error. But this is not a language feature, and we can't do this at compile time from the library. So the best that the library can do is, at creation time, institute a fail fast policy, where when it's actually creating and populating a set or a map, then it has the opportunity to check for duplicates at that time. And if it detects one, basically the question is what policy should be applied there. And so basically we've decided to make that be an error because it's most likely a programming error, and it'll catch errors sooner at creation time instead of having some odd behavior occur sometime at runtime. So like I said, most other languages are last one wins. In my survey, I found that there are a very few number of programming systems that reject duplicates in this fashion. And so Clojure is one. Actually, Clojure has two means of doing it. There's a syntax that does reject duplicates, and then you can call some kind of constructor, and that has a last one wins policy. And ECMAScript in strict mode will reject duplicate keys if you specify them. All right, so here's an example of that. So here is a slightly modified example, which is almost the same as one in the previous slide, but see if you can detect the duplicate. Yeah, okay, so there are few people that have sharp eyes here. So there are two entries that have colon as the key. Now, so you can imagine, though, if there were a lot more entries and you're fixing a bug on a deadline at 1 a.m., it'd be pretty easy to miss. And so if somebody said, oh, you need to change the entry for colon to some other value, it's very easy to imagine you editing the wrong one and then banging your head against the debugger for a while, wondering why that the value didn't take effect. So anyway, instead of having last one wins, or worse actually, is some undefined policy where one of the values will be chosen, we've decided to make this be a fail fast error at runtime, at creation time. All right, so let me step away from the API a little bit and talk about implementation issues. And I think the main thing here is about space efficiency. So let's take an example where we take a hash set and add 2 strings to it. So here, now there's this weird thing about load factors and number of buckets and so forth. In order to do this without resizing, we actually have to pass 3 to hash set. So basically, we create a new hash set and add 2 elements to it, and then we wrap it in the unmodifiable wrapper, like I mentioned earlier. So that's the way to get the equivalent of an immutable set in core JDK libraries today. So how many objects get created when you do this? Okay, so there's the unmodifiable wrapper itself, there's the hash set, but it turns out if you look at the implementation of hash set contains a hash map where the keys are the set members and the values are just some sentinel object. So there's a hash map in there as well. Now, if you look inside the organization of a hash map, there's an array, which it calls the table, which is an array of objects. And then the actual elements that are members are contained in node classes, or node objects, and so now we're up to 6 objects, and there's 1 node created for each element. All right, so here's a diagram of that. So we have our set variable. It points to the wrapper, the hash set, the hash map, the table. The table contains 2 nodes, and each node contains references to the actual set element, which is the string, and then the sentinel value, which is called present. And so that's the same value for every object, because this is just a set, and the value is irrelevant. All right, so how big is this? So I made some quick calculations here. This is not necessarily very precise because it depends on a bunch of things about what architecture the JVM is, 32 versus 64-bit and so forth. But I made some assumptions about this. The first thing is every object in Java has depending on the exact circumstances, but in this case, if you have a 64-bit JVM with compressed OOPS, each object has a 12-byte object header. So that's just overhead. There's also the fields in the object, and most of these are 4 bytes. So an object reference is 4 bytes if your heap is small enough. And things like an int or a float are also 4 bytes. So if you count these up, we have 6 objects, but each has several fields. In particular, the hash map has 6 fields, which is rather more than I had expected. And each node actually has 4 elements, because there's not only the key and the value, but there's also a next pointer and then the hash code for quick hash checking. So it turns out that in order to have a hash set with 2 string elements, it takes 152 bytes and 6 objects, which is really a lot of overhead. Because if you think about it, 2 string references is just 2 object references of 4 bytes each. So the payload is actually 8 bytes, but it takes 152 bytes to store that. So that's pretty bad. All right, so we can do a lot better than that. Actually, it's like shooting fish in a barrel, quite frankly. It's really easy. So let's say we create an immutable set implementation that stores 2 elements in fields. So it takes 1 object, and we store the elements in fields. And so you see the diagram at the bottom. We just have 1 object that takes only 20 bytes or so. And so the point here is that by creating immutable collections, that we have a lower fixed cost. So just creating one of these collections has a certain amount of overhead, and so that fixed cost is lower. And then instead of having separate node objects, we can add more fields or use an array. And so the variable cost, that is the cost per element, is much smaller. Now, you're saying, well, what good is a set with 2 elements? I mean, what if you have 1 element or 3 elements? So the design of this API is intended to keep all of this private inside the library and have a bunch of different private implementation classes that are chosen by the factory method depending on a variety of criteria. So we might have, you can consider several different kinds of data organization. For extremely small collections, you might decide, okay, let's just have a couple of fields and not have an array at all. So if we have a set of 2 elements, which might be very common, let's just store those directly in fields in the object. And in fact, we don't even need to store the size, because this is a special case set object that knows that it has exactly 2 elements. Now, there's a bunch of these little things where you might have a set with 0 elements, a set with 1 elements. So we're probably not going to have too many of these, but for the space advantages for the extremely tiny sets and lists and maps is very advantageous. Now, if you get bigger, you might say, okay, at a certain point, you don't want to write, field with. You don't want to have a field-based implementation that contains 18 elements or something like that. So at a certain point, you might say, let's fall over to an array that is of exactly the right size and then do linear searching on it. And it turns out that linear searching, oh gosh, you don't want a linear slowdown for that. But there's a very complicated trade-off between, say, a linear search and a hash-based search. And I don't know exactly where the trade-off is. My guess is that it is somewhere between 6 and 8 elements, but I'm not sure. We have to do some benchmarking on that. So there's another approach, which is to have an array-based scheme, but then it does closed hashing, but you need to leave enough space in there so that your closed hashing can work effectively, because there are going to be collisions in it. And then for really big things, we might just decide to fail over to a hash map internally. Although it's not clear to me that's necessary, but that's an option that we might provide. Anyway, the point here is that we can have a multiplicity of different implementations, and they make different space versus time trade-offs. And the library is in the best position to make those trade-offs. Another point here is that if you looked at the organization of a hash set before, it had 6 objects. And so that required a lot of pointer chasing. And so one of the problems with modern computer architectures is that if you have a pointer to something, if that's in a different place in memory, you might take a cache miss. And so looking at an element in a set, even if it has only 2 members, might involve several cache misses, and it might end up taking quite a bit longer than you might expect. And so simply by creating fewer objects and putting things in the object itself, instead of having arrays and nodes and structure of nodes and so forth, will improve the locality of reference, and we hope improve the access time considerably. So the idea here is that we'll have all these different implementations, and they're all going to be private APIs. And so the only thing that the programmer sees is set.of or map.of. And the implementation will be chosen by the library, and it'll be an implementation of some internal class. And probably, I think collection size is the primary criterion by which an implementation will be chosen. But we may take other things into account. For instance, if a 32-bit JVM versus a 64-bit JVM might have different size characteristics and might change the trade-off point between a field-based implementation and an array-based implementation. So we need to do some more investigation there, and we also need to do some more research about what thresholds at which we'll switch from one implementation to the next. Now, the idea here is that if these are all kept private and opaque to the application, that we can change those in the JDK at any time, possibly even in minor releases. And the idea is that all these implementations strictly adhere to our classic list, set, and map implementations. So the application can't tell when it gets a different implementation, mostly. We'll talk about that in a moment. But anyway, the idea is that we can change these compatibly in any release, possibly in minor ones. Well, now there are a couple wrinkles that let the implementation show through. One is serialization. And so if you're familiar with serialization, actually the first thing is everybody hates serialization, but the fact is everybody uses it too. So I think we have to make sure that these implementations are all serializable. But if you do take the straightforward approach of serializing something, the internal structure of the object actually leaks out into the serial form. And that's actually a compatibility issue for the JDK. So we have some things where we would like to re-implement some classes, but they are locked into their current representation, including the name, even if they're private classes. And they're locked into all of that because a serial form exists externally that applications are actually using. And so that's actually another axis of compatibility that we have to contend with. So the approach we are intending to pursue here is to create a serial proxy class. If you look at Josh Bloch's book, Effective Java, he talks about using what he calls the serial proxying technique. Basically, instead of serializing as itself, if you serialize one of these collections, it will create a proxy class, load the data into it, and then serialize that. And exactly the opposite thing happens when you deserialize. So when you deserialize one of these things, the proxy will say, oh, okay, I'm actually an instance of that implementation over there, and then recreate it at runtime. So another way that implementation details can leak out is via iteration order. So if you now, this only applies to sets and, well, hash-based sets and maps. And so if you read the documentation, you'll understand that the iteration order of these structures is undefined. But it turns out, in actual practice, that the iteration order for these is pretty stable. And since things like strings have really bad hash codes, the iteration order is often very, very predictable. So if you put one-letter words in, like set.of A, B, and C, the iteration order is actually A, B, C. I mean, so it's pretty bad. Now, it turns out that, yes, the specification says iteration order is undefined. Programs must not rely on specific order of iteration. The fact is, this happens all the time. And so it's very easy. In fact, it's happened inside the JDK. We actually have had some problems where we changed one of the data structures to have a different iteration order, and a bunch of things broke, and it was really painful. In fact, I think we had to go change it back. And so this is a problem because the iteration order is supposedly unspecified, but it's actually very stable, which leads programs to make inadvertent dependencies on that order. But then we go to change it, and it breaks a bunch of stuff. So that means that there's resistance to actually changing it. So that's a real problem. And, well, actually, what's really the problem is there are times when we actually do need to change the iteration order. So, for instance, in Java 8, the internal organization of HashMap changed under certain circumstances to be each hash bucket became a tree instead of a linked list. And so that changed the iteration order, and that was unavoidable. So that exposed some programs that inadvertently had dependencies on ordering, to different behavior, and it caused those programs to break. So in the previous slide, I was talking about, oh, we can have all these different implementations, field-based, array-based, hash-based, and so forth. And the library is going to choose one of those, and the application doesn't get to choose which it is. Well, if the library chooses, then that means that the iteration order is going to be unpredictable. And I think that's a feature. And so in order to make sure that's unpredictable, we're going to add a random number to the hash code so that the iteration order is randomized. Now, ideally, if we really want to flush out bugs in application code, we would change the iteration order on every single iteration. But that's actually a little too much overhead. And so probably what's going to end up happening is that the iteration order will be fixed for a single run of the JVM, but each different run of the JVM can have potentially a different iteration order. And so the idea here is to kind of toughen up application code so it doesn't inadvertently build in order dependencies on iteration. And so if you accidentally write that code and you have tests, maybe your test will pass once, but if you run the test again, look at a different iteration order and it'll break pretty fast, we hope. So that's the current idea here. Now note, actually, this randomized iteration order idea is applying only to the new collections implementations. The existing collections implementations will retain their current behavior. I think it would be a pretty aggressive move to make them have randomized iteration order as well. And I think that's an interesting idea to talk about, but that's not on the table at this time. All right, so there's life in the old collections framework. So Java 8 had lambdas and streams. Java 9 has modules, but the collections framework is still there. But we're still working on it. So if you look at my other talk, there's a lot of stuff added to the collections framework in Java 8. And so what we covered in this talk was a new set of APIs and immutable collection implementations that provide space-efficient and convenient collections to applications. So I have a couple references here. There is the slides for my Java 1 talk a couple weeks ago are available at that link. And then JEP 269, which is the JDK enhancement proposal, is also available at that link. So thank you. I have a couple minutes for questions. We can open it up for questions and comments. Right here, sir.
You mentioned that those immutable collections won't be available in the public API directly. But is there going to be a kind of builder API that you can say, I want to build an immutable list, and that you can fill it in a for loop and then tell the builder, give me the immutable list?
Okay, so the question is, so the implementations are not going to be available in the public API, but is there going to be a builder? No. So now, I think that's an interesting use case, and we might consider it. Kind of the escape hatch for that is if you want to create an immutable collection with a list of objects that is computed, then the way to do that is to create an array containing those elements, and then call one of the array call one of the factories that takes an array. Okay, another question? Right down here.
Optionals? I mean, if you pass optionals to the builder, or to the...
Well, the question is about optionals, but what about optionals?
Will it create a list of, will it unwrap the optional, or will it...
Okay, so no, there's no special case handling for optionals. If you create a list of optionals, you get a list of optionals. For a variety of reasons, I wouldn't recommend that, but I mean, if you really want to create a list of optionals, you just get a list of optionals. Another question. Right here, sir.
Does the set of list implementations the API has overloads for the fixed args and the var args. What is the reason for having the fixed arg overloads?
Okay, so what's the reason for having the fixed args overloads? So basically it's efficiency. And so if you look at the way that var args are implemented, then the compiler generates some code that says, okay, well, there's a certain number here, and so it generates a bunch of bytecodes that creates an array and then loads those values into the array. And then on the callee side, the callee gets an array, and then what's going to happen is that those are going to be copied out. And so with fixed args overloads, there's a direct path because the overload, if there's an overload with 3 fixed arguments, it knows that it's creating a list with exactly 3 elements. And so it can take a shortcut there, and that bypasses some copying and memory allocation overhead. Hey, one more question. That up there. Yeah. Okay, so the question was why didn't we just adopt Guava? And so we talked to the Guava guys a fair amount. In fact, we don't talk to them enough. We've taken some ideas from Guava, and I think we will. I shouldn't say taken. We collaborate with the Guava team, and we share ideas and pick up ideas where it makes sense. And so one of the things is that Guava has a very large set of collections libraries and implementations, and we've considered picking it up, but it's not a matter of taking all of it. We might want to take some subset of it. And in fact, this is sort of like taking some subset of it. One of the responses has been, oh yeah, well this is just like Guava's such and so, such and so. One of the aspects of the Guava collections is that they have immutable types in the type system. And so, whereas here we just say set of something and we get a set implementation that happens to be immutable, Guava you can say, I want an immutable set of, and so that's actually in the type system there. And so, but if you, well, it's a little bit too detailed for this, for the 30 seconds remaining. But if you look at their class hierarchy, it's actually a little contorted, and I understand why they ended up the way they did, and they had good reasons for doing that. But it makes things a lot more complicated. So instead of just taking Guava or trying to do some engineering of factoring out little bits of Guava, I think we're taking some ideas from Guava. And in fact, a couple guys from Guava have reviewed this API and we've been discussing it. So I think there's definitely some influence there, but it's really not a possibility to just take all of Guava and adopt it. So my time is up. Thank you very much for your interest and attention.